Now we are ready for topology optimization. We have geometry available to create our base FEA from, and very importantly, we have load cases available. So these are the two things that we need: the geometry file as a base for our mesh that we're going to use, as well as our loads that we're going to run our topology optimization on. The topology optimization stage of this project actually consists of two parts. The first part is to create the initial mesh that will be used for the topology optimization, and the second part will be the actual topology optimization. In this example, I'm going to use two products. I'm going to use MSC Apex as well as Patran and Nastran. I'm going to use MSC Apex to create my base model from, as well as those interface points where the attachments will be, as well as the mesh that I will then export into Patran, where I will continue setting up the topology optimization. I could have done everything in Patran, but I would like you to become familiar with the MSC Apex environment, which is a brand new product platform which will develop very quickly, and over the next few years will eventually replace Adams as well as Patran and Nastran. But for the time being, I'll use it as an intermediate step, because some of the things that I need to do is actually quite convenient and useful to do inside Apex. So here I have Apex opened, and the next thing to do is to import the geometry that we have exported in the previous example. So this is the rocket geometry that we have exported from Adams. To use a solid mesh for topology optimization is not a very economical thing to do, especially for simple parts like this. A part like this can also be represented by a sheet or shell elements instead, where we have the thickness specified rather than visually represented. So to make a more economical model, I am rather going to create a mid-surface model and represent the flexible body with shell elements instead of solid elements. To do this in Apex is a very simple procedure. We simply use the option under Geometry Edit Tools, and you can also watch this video which pops up when you hover your mouse for a second over here. And for a constant thickness body, it's quite simple to simply click the body and you can see a mid-surface has appeared. Now I don't need to use the solid anymore. I can conveniently hide it over here. What didn't come through from the Adams export was the location of those nodes. Fortunately, we have it reflected in our little table over here, and I can purely copy and paste it, knowing that my units are in meters. And that is if Apex was set to meters as well. If not, I just need to mentally make that conversion. For this process, I will create points at the locations that I need specified. So for the first location, I have an X value of minus 30 millimeters, Y value of minus 200 millimeters, and 300 minus 300 millimeters, and a value of 0 for the Z. That creates the first little point there, and visually we can see that is indeed the correct location. For the second point, also reading it from my text file, or you can read it off by looking at the information at the relevant marker. You can also see those values over there. I can specify my X location as 400 millimeters in this case, 250 millimeters, and again Z as 0. That brings us the second point, and for the third one, minus 300 again, 300 again, and there we go. Right, so now we have a surface to mesh as well as points where we need interface locations. Now, to make sure that we do have element nodes at those locations, we are going to use the seed point feature, which enforces a node at those locations. It's very important to read the instructions over the screen here. First, it asks us to select the points or nodes and then click the middle mouse button. So I'll select the nodes and click the middle mouse button, and now it asks us to select the edges or faces and then click again to complete the process. So now I click the surface to which those points need to be associated. So important, I need to get to a stage where I see those three triangles, and those are important because when I'm going to mesh with these elements, and I prefer using quad elements like that, I really want to see that I have an element with a node at that location. This mesh is a bit coarse for topology optimization purposes, so I will refine it again, and this will be a better mesh. A much coarser mesh will give you something terrible looking like this, which is not usable at all. So I'm going to stick with a refined mesh like this, and this is the mesh that I am going to export. Now when we get to the pattern side, it may not be that easy to identify which of these nodes are the ones that represents those interface points, and those locations are very important because we can't define locations incorrectly, otherwise our analysis assembly won't work so well. So to make it easier for us to identify these points afterwards, I'm simply going to randomly create loads at those locations, purely to get the node IDs of these nodes in this model, so that I can assign these values to them. Because on the FEA side in Adams, they had these ID numbers, but they won't have the same ID numbers on this side. So we need to make sure when we import this file into Patran that these forces are applied at the correct locations. And we're going to do that by replacing these numbers with the new node IDs that we will get from this file, but I'll show you in a moment how we're going to do that. So first of all, I purely want to make sure that I create a force with a specific value at these different locations so that I'm easily able to identify these locations later. So on the force moment form over here, we are going to add a force and going to specify a force by components. Let's just, it really doesn't matter, it's purely for identifying these applied nodes. So let's just apply an arbitrary load of 100 at this location over there. So that would be node 1. Well, in fact, to be honest, I remember when I created these, and this is going to make it easier to know which is which. This was the first node to be created, that was the second one, and that was the third one. So let's rather stick with that arrangement. Use a value of 100 at the first location over there. Create another one with a value of 200 at this location over here, and then for our third one we are going to use a value of 300 over here. And as I said, these values have no meaning whatsoever because we're going to make sure that we don't use it on the optimization side. This is purely to help us identify the new node IDs of those nodes. Right, so now I have some thickness values over here. The thickness was automatically calculated from the original geometry. I just need to specify my material, and this is quite important. So This can be steel. I'll have a density of 7850 e to the minus 9 because this is kilogram per cubic millimeter, and a Young's modulus of 200 gigapascals. I'm specifying this in megapascals, so it's 2e to the 5 megapascals, which is 2 gigapascals, and a Poisson's ratio of 0.3, and simply assign it to this body. One other step that I just need to specify is the bending stiffness behavior. Purely just assign it over here, and this is just to complete the picture that we have a stiffness or bending stiffness behavior, we have a material assigned, we have temporary loads assigned, we have a thickness assigned, and we have our mesh. Now we're going to export the mesh, and we can do this at the part level or at the file level, because at the file level we only have this single part, so it really doesn't matter which option you choose. And importantly, we're going to make sure that we export a Nastran file. So this is the file that we are going to use for optimization. Mesh for optimization. And there we go, and we're going to look at that file in a moment's time. Just make sure that we export it into these units. This is the same units that we've used on the Adams side, so Apex will convert it back to the units that we've used on that side. Right, so now going back, we can have a look and find our BDF file, mesh for optimization, and also use Notepad++ to look at what we have over here. Now this is the information that we've now exported. These are all the elements, and right at the bottom here we will find the material information. Now just to make sure, I need to see if we have force files, force entries. So these are the force entries. Now the important thing to notice is that we want these numbers to be the same as the numbers we have for the loads. So on the one side we have node IDs that defines the loads from the Adams side, and on this side we have a new mesh with new IDs. Now it's quite normal that these values are quite high because of the high number of elements that we have created. There are two ways of fixing this. So we could either change the node IDs for this large file if we can find them, or we can change it for this file over here. Now I actually find it easier to do it in the user interface. That way I can make sure that I do it correctly and that I don't have any problems when assigning the loads. So if I'm not going to edit the files, and the reason I don't want to edit the files is the files are extremely sensitive for the location of numbers. These numbers are in specific blocks of data, and if you by accident delete a space and these numbers shifts left or right, you might have a problem. So we're rather not going to edit these files if we don't really need to or have to. So I'm going to rather change these node numbers in the user interface after importing this model to be the same as these numbers that we have in the front of here, and I'll show you exactly how we're going to do this in the next step using Patran.